Welcome back. In this class, we're going to talk about the solubility of substances in different solvents, particularly the solubility of substances in water, because water is a really good solvent. So if you can remember that water is a polar solvent, then that will actually have lots of implications for whether something is going to be soluble in it or not. And we'll talk about the intermolecular interactions that allow something to be soluble in water. Now, if you were asked to explain, is something soluble in water? Yes or no, and explain why. This is the structure that your sentence has to follow. Number one, because it said, is it soluble in water? You need to make a statement about the water. Water is polar. That's grand. Next, that's not enough though. You also need to say that whatever you are asked about, whatever the compound is, you need to state, is that polar or non-polar? That's the next one. Now, if you do the two of those, both of them must be present. It's not enough. Please don't be the lazy person that goes, they're both polar. No, it will actually be on the mark scheme that the word polar will have to be there twice. So please spell it out for the examiner. Don't be lazy here or it's going to cost you 3 marks. So we get 3 marks for saying water is polar and X is polar, whatever X is. Then your next statement is to make a statement about the intermolecular forces. So if X is polar, then it can form hydrogen bonds with water. So that idea about hydrogen bonds and soluble will get you your next 3 marks. If you said in the first part that X is non-polar, well then it can't form hydrogen bonds with water. And you need to state that. Now, I'm going to say something here, and it's probably something that you've all heard 10 times before to put in a solubility question. And I'm telling you, no. Please don't write this on your exam paper. If you've ever come across the phrase, like dissolves like, and you leave your answer like that and just go, oh my God, I get 6 marks. No, you don't. The chief examiner has stamped that out. It happened about 4 years ago. That is not an acceptable answer for explaining solubility. So please don't use it. It actually builds really bad habits. This is what a perfect solubility answer looks like. So this is the one I want you to give in your exam. Now, I know what you mean. So I get it. I've been teaching a long time. I know what you mean when you say like dissolves like. This is what you mean. You mean that a polar solvent dissolves a polar substance. You also mean that a non-polar solvent dissolves a non-polar substance. Or a non-polar substance is not soluble in a polar solvent. So that's what you mean by like dissolves like, but that's not what you said, because polar is a key phrase that has to be in your answer. So we need to expand this a little bit more to get you more marks. Now for a solubility question, let's deal with polar substances. Okay, so if you're given a random substance like ethanol, and you're asked, is ethanol soluble in water? It absolutely is, because that's what the 12% volume per volume on the back of a bottle of wine means. The 12% is the ethanol, the rest of it is water. So here, when you look at the ethanol, it is polar, and we did this previously. You've delta minus on the oxygen, delta plus on the hydrogen. If I draw a molecule of water close by, you have delta minus on the oxygen, delta plus on the hydrogens. You have opposite dipoles nearby, so they will attract each other. Oops. A delta plus to delta minus force of attraction like that, and that is called a hydrogen bond. Even though the molecule is not bonding to or interacting with itself, it doesn't matter. It is interacting with another polar molecule, and it is a hydrogen bond. Does it have an oxygen? Yes. Is there a hydrogen attached to that oxygen? Yes. Therefore, it's a hydrogen bond in between the 2 molecules. Now, where students kind of fall down a little bit, in ethanol and water, there is an OH here and an OH here. You can have a situation with polar molecules where only one of the 2 has an OH. So if I was to look at ethanol, so ethanol is that, And we have water. Like that. Now we know water is polar. We have delta minus and delta plus. The CO bond is also polar. You have a delta plus to delta minus interaction. Now here, that is still considered a hydrogen bond. Now when we did aldehydes in the previous class, when we talked about intermolecular forces, one of the first practice questions I went through had an aldehyde in it. And I said aldehydes form dipole-dipole. Yes, when they are interacting with themselves. So if I had two aldehyde molecules close by, then they will form dipole-dipole with each other. Like this. But because of the water, that there, delta plus to delta minus, that is dipole-dipole. However, over here, it is hydrogen bonding. Because, looking at the structure, there's an oxygen here. Is there a hydrogen attached to that oxygen? No. But there is one here on the opposite molecule. You have a hydrogen attached to an oxygen, leading to the bigger dipoles and the stronger interaction with it and the next molecule, which is, in this case, the aldehyde. That is a hydrogen bond. There are some families of compounds that will form dipole-dipole with their own molecules, but hydrogen bond with water. Aldehydes and ketones are the top examples of that, technically esters as well. Okay, so that's really important. So just because it's an aldehyde and has dipole-dipole with itself doesn't mean you can say that it's not soluble in water, because it actually is. The smaller chain ones are soluble in water. Now, down the bottom of page 147, there's an experiment for demonstrating whether or not a solvent is polar or non-polar. Now, it's not a mandatory experiment, but it does come up in the exam, and you have to be able to describe what you see. So we take a burette, like the ones you used in your titrations. You clamp it vertically in a retort stand. You put a beaker or something underneath, it doesn't matter, as long as it catches whatever the solvent is. And you fill your burette with whatever your solvent is. We're going to test a polar solvent. Now, if I asked you, give me an example of a polar solvent that is free and I'm not going to have to pay for it and it's really easy to get. Water. So you would fill the burette with water because it is a polar solvent. Then you open the tap on the burette and you allow the water to flow out. Now, water is polar and it has the charges. That's what being polar means. It has the delta plus and the delta minus charges, partial charges. So that's going to interact with something that is charged. So what I do is I bring a charged rod close to the stream of water. If I was to bring a negatively charged rod close to the stream of water, is there anything in the water molecule that will be attracted to the negatively charged rod? Yes, there is. What will happen is the water molecule will rotate. It's going to spin. And then we end up with this situation where you have your delta positives like that, and they will be attracted to the negatively charged rod. So what you will see when you're doing the experiment is the water stream deflects towards the rod. That phrase, the stream deflects towards the rod, that's important for 3 marks. Now, if I was to change the charge on the rod, say for example, I was to bring a positively charged rod close to the stream of water. So keep the burette open, but now we change the charge. Now, a lot of people here will say, oh my God, it has to repel, it must go the other way. No, it doesn't. It is the same result because the water molecule can spin the other way. And now you have your oxygens pointing towards the positively charged rod, like that. And the positive charges are pointing away. And now the delta minus on the oxygen is attracted towards the positively charged rod. So the exact same thing is observed. The water stream deflects towards the rod. So learn that off, that the stream of water deflects towards the rods for both positive and negative. Now, as your control, you can put in a non-polar solvent. So a prime example of a non-polar solvent would be cyclohexane. Now, hopefully you came across that in the gas laws. but you should be able to name a non-polar solvent. Cyclohexane is the most common one that we come across in Leaving Cert. You open the tap on the burette, let the cyclohexane flow out, and it doesn't matter how close you bring the negative or the positive rod to that stream of cyclohexane, absolutely nothing happens. There is no deflection. Why? Because it's not charged. Cyclohexane has this structure here. Hex for 6 carbon atoms. Cyclo, meaning it's in a ring. And then we have all carbon-carbon single bonds and hydrogens attached like that. So all of the bonds in that molecule are non-polar covalent. So it is a non-polar solvent. Okay? Now, be able to describe the results from this experiment. You're not going to have to draw it or anything like that. Just be able to tell me what happens with the results. Now, let's look at some practice questions. So for worked example number 1, explain whether you think ammonia is soluble in water. Draw a diagram to support your answer. Now, as a dead giveaway in a worked example like this, if the examiner wants a diagram, then it is soluble because the examiner wants you to show that. Why is it soluble from your diagram? So we've got a bit of a head start here. Well, we're going to go back to the beginning. So for worked example number 1, ammonia is NH3. From my dot and cross diagrams, nitrogen is attached to 3 hydrogens, and we have this lovely pyramidal structure. Now, it hasn't mentioned anything about showing shape, etc., so don't get hung up on your bond angles or any nonsense like that. Nitrogen has an electronegativity value of 3.04 and hydrogen is 2.2. 3.04 minus 2.2 is, not in a million years am I going to do that in my head, is 0.84. So that is a polar covalent bond between the nitrogen and the hydrogen. So if I was filling in my partial charges, the nitrogen is delta minus and the hydrogen is delta plus. And it's the same for all of your hydrogens. Therefore, that will be delta minus 3. There we go. Now, so when you're starting off your solubility question, we're asked, is this soluble in water? So we make our first statement. 1, water is polar. Now I've just worked out my second statement. NH3 is polar. There's my first 3 marks. Talk to me about the interaction. So if they're both polar, can they form hydrogen bonds? Yes. So number 3, NH3 can form hydrogen bonds with water. And because it can form hydrogen bonds with water, therefore NH3 is soluble. Now, to be honest, I would make that statement anyway. Normally in a question like this, it's for 6 marks. Is it soluble? Is it not? And explain why. Because students do not do well with this question. Don't forget to say whether it is or it isn't soluble. You could lose half the marks for this question if that is asked. So put it in anyway. Get in the habit of putting it in there. So you're not going to be the one looking at your exam paper next August going, oh my God, it's the one thing she told me to do. So make sure you get in the habit of doing it now. And there is your picture perfect 6-mark answer. Now, if I was showing this on a diagram, we need to show the delta plus to delta minus interactions. So we draw water. You show the delta minus, delta plus. Don't worry about balancing your charges. And then you have a delta plus to delta minus force of attraction, and we label it as a hydrogen bond. There we go. So 3 marks for my diagram. 3 marks for water is polar, NH3 is polar and can form hydrogen bonds. And then 3 marks for saying that it is soluble. So it's a lovely question to get, and this type of a question can come up anywhere. So be particularly vigilant in the organic topics as well, particularly question 8 for a question like that. Now, let's have a look at some of the practice questions. We're just going to do one because I always ask students this one, and it is in relation to iodine. Okay, so this is question 10 on page 160. Now, biology, oh, this is question 10, not page 10. Biologists, be careful here. I'm setting a trap for you. Question 10. Iodine solution is used in biology to test for the presence of starch. It is also used as an indicator in the sodium thiosulfate redox titrations, which is unit 3. Predict and explain whether elemental iodine, which is I2, is soluble in water. It's a trap. Be careful. Right. Go after this like a normal question. So we're going to decide, is it polar? Is it non-polar? So if I draw out iodine bonded to iodine, they have the same electronegativity value, which is 2.66. The difference in electronegativity is 0. Therefore, iodine is non-polar. Oh wait, that's going to be a problem. Water is polar. But now we've just said previously, non-polar substances are not soluble in a polar solvent because they're not. Elemental iodine is absolutely not soluble in water. I2 can't form hydrogen bonds with water. Therefore, it is not soluble in water. Now, that orangey red solution that you use in biology and as our indicator, that's where your iodine has been mixed with a little bit of potassium iodide. Now, there is a page on this a little bit later in the titrations, but elemental iodine, they look like little pellets, like little silvery balls, like, what do you call them? Ball bearings. They're these tiny little round spheres that are grey. If you put that into water and give it the best shake that you can, absolutely nothing is going to happen. It doesn't dissolve. Why? Because it's non-polar. It can't dissolve in a polar solvent. You put it in cyclohexane, it will dissolve. But to get iodine to dissolve in water, to have your indicator solution and use to test for the presence of starch. Right. What you actually do is you put it in a solution of potassium iodide salt. Potassium iodide is like sodium chloride. It's a salt. No, we don't eat this, so don't lick it if it's in the lab. It's toxic. This splits up and dissociates in water into K plus and I minus ions. So when you dissolve it, it's forming these ions. Now you will have I minus ions floating around inside of the water. When you put I2 into water that contains I minus ions, the iodine combines with the I minus ions. Technically, it's in equilibrium. Don't worry about the equilibrium symbol for now. And you get I3 minus, which we call the triiodide. This is what you have in that red-orange liquid that you see and we call an iodine solution. It's the triiodide. It's not I2. Be careful of that in the exam because, again, if it was me and I was setting a trap, particularly for my 5th years, actually, I will ask about that. I'll ask about the iodine because you'll all remember the iodine solution from biology and from junior cycle and as your indicator from your redox titrations, and I'll go, let's see if we actually know what's happening here. So be careful of questions like this. Now, there's plenty of other practice questions going through, is it soluble, is it not? So make sure you go through those in your practice questions in your notes and you'll be absolutely fine for a solubility question.